Hi guys, today we are going to begin topic 5 of AP Chemistry. This is chemical thermodynamics. Now you may recall that our second topic was thermochemistry, so that was dealing with energy changes, and we introduced two concepts that we want to go into a lot more depth with here in topic 5. Now you may recall that we discussed the a specific system has both heat content and it has disorder. So the term entropy refers to the disorder of a system. Enthalpy refers to the heat content of a system. Now, it might be safe for us to assume if we have a system that is getting uh, an energy benefit, if we're going from a higher energy position to a lower energy position, that would be favorable. We're becoming more stable. This is a discussion that really deals with our delta H, our enthalpy content of the system. Now, if we have a negative enthalpy, that means that we're going from a high energy to a low energy, and that's a favorable situation. Nature tends to have releases of energy being the favored situation compared to gaining energy. So one of the things that we see though is even though this enthalpy change, this delta H, could be negative, okay, which means it's favorable. Even though a reaction might show a negative delta H, sometimes this reaction still doesn't take place. To consider that, what we want to do is we want to remember this concept of activation energy. Even though we may start at a very, very high energy position and we may end at a very, very low energy position, we need to have a little bit of energy to go into the system in order to make this reaction take place. Well, if the difference between our starting energy and the ending energy, which we call activation energy, if this is a really, really large amount, it may prevent this change from taking place. So again, we just want to consider that even though the enthalpy content may seem favorable, a reaction still might not occur if it has a very high activation energy. An example of this would be oxidation of ammonia by oxygen. When you look here, you'll notice we have our ammonia reacting with oxygen to make nitrogen monoxide and some water vapor. When you look at the process though, you see that we have a delta H given that is negative, okay? So this means it's releasing heat. The enthalpy value is very favorable here. It's going to become more stable as the nitrogen monoxide water products than it would be in the ammonia and oxygen forms. But this has a very, very high activation energy. So, and if we were to diagram this and we look at the energy content of the system over the time that it takes to react, what we would see happening is we start at a high position, we end at a low position, but we have a very, very high activation energy required to get there. So that high activation energy prevents this process from actually taking place. We could make a second assumption that if we see a positive delta H, so again, if it's a positive heat content, we have to add heat in order to make a reaction take place. This should never ever occur. But sometimes in reality, we do see these endothermic reactions. So there has to be some other explanation for why this would occur if the heat content is not favorable. If you look at something dissolving, so this is an example of a common salt, this is potassium chloride. As our potassium chloride dissolves, notice that we're going from a fixed solid state into a spread out aqueous state. The enthalpy change here, this delta H, is going to be a positive value. So it's going from a lower potential energy to a higher potential energy, and that's counterintuitive. Bonding and chemical reactions normally take place so that we can make a system more chemically stable. So there must be a missing piece. The thing that we want to bring to bear here is that energy is required for all processes. And in this case, we're seeing that some energy has to be put in. But the thing that we want to talk about now is the disorder of the system. So we start with this solid, which is very, very organized, and we're turning it into an aqueous state which is going to be a lot more scattered. Okay, these particles are further away from each other and they're able to freely move instead of being locked into position. The amount of disorder, again, is what we refer to as entropy, and we give it the symbol S. So you might see something called absolute entropy, and that is the entropy of a fixed system that's not changing. If you talk about the entropy change, that is going from one absolute entropy to a new absolute entropy, and it's the change that takes place. We give that a delta sign to indicate a change in entropy. Well, since we're going from an organized state to a less organized state in this process above, what that tells us is we are increasing entropy. We have a positive delta S for this process, and that is going to be favorable in nature. One of the things that I want you to really emphasize, to understand here, is the idea that the states of matter are very, very simple entropy comparisons. When we look at a solid, we know that it's fixed, it's organized, it's compact. A liquid is going to be compact, but it's able to move around more. And then a gas is very spread out, and those particles are able to move even more. So as I compare the different states, we know that solids have the least entropy, liquids are in the middle, and gases have the highest entropy when we're comparing just states of matter. A thermodynamically favorable process is any process that we sometimes say it's spontaneous. These are processes that will occur because we have an overall energy, not always a gain, but I mean, we have a better energy position is a better way to look at it. You end up with a better energy position, and this thing becomes thermodynamically favorable. So looking at our states of matter, recall that a solid is this highly organized fixed set. A liquid is close together, but not nearly as organized. And then you have your gas state where the particles are very, very spread apart. So the entropy, if you look at this graph, it's entropy versus temperature of a substance. As we have a solid, as you increase the entropy, the temperature will rise and vice versa. If I heat the solid up, the particles are going to start jiggling faster, they vibrate more in space. Once you hit a breaking point here, this specific melting temperature, then we start breaking apart from the solid into the liquid phase, and that's going to increase entropy even more. Then we get to this point where all of our liquid is now higher energy, higher temperature, an increase of entropy, and it's going to get to this next breaking point, which is our boiling point temperature. At this point, the bonds are being overcome that hold it together as a liquid, and it becomes a gas. So this is going to be a very, very large entropy increase without a temperature change. The energy is all being used to separate the particles and increase the entropy. Now, we've talked about states of matter. Now we need to talk about the number of particles that are present. If you have 1 mole of gas particles compared to 2 moles of gas particles, the larger number of particles has more possible positions and more randomness and more scatteredness about it. So we would say that the more moles of a substance you have, the more entropy would exist within that system. Now with gases, we can look at the volume that a gas is in order to consider its entropy. If you have a small volume, then there's less potential space for the gas to move around in. If it's in a large volume, there's more potential place for it to move around in. So we have an increase of entropy if you have an increase in volume of a container that a gas is held in. Temperature, as you probably saw in the last graph also, as temperature rises, the entropy of the system rises because these particles are moving faster and they, again, have more potential places that they can go. Now here in our first task, you're meant to predict the sign of delta S. You need to take a look at the states of matter. I'll give you an opportunity to work these out, and then we can review them later. In our second question, we're trying to determine what has more enthalpy in each of these scenarios. So you have a metal at a 273 Kelvin temperature or a 400 Kelvin temperature, consider that factor. A flexible soft metal like lead or a diamond, which is a rigid solid. So again, think about how the particles can move. And then lastly, two samples of the same gas, but at different pressures. You can consider volume with pressure differences also. Now, let's talk about how we can bring math into this picture. So first, the change in entropy, that delta S value, can be determined as essentially the ending situation minus the starting situation. Okay, final minus initial, that's change. So if you're given absolute entropy values, you can determine the overall change based upon those absolute entropies of products minus the absolute entropy of reactants. You might be familiar with this equation because it looks just like Hess's law, which we've already dealt with in the past. Hess's law says the same thing, but with enthalpy instead of entropy. Similar concept though. If you take the ending minus the beginning, you find a change. So I want you to look at this scenario, and we're going to actually apply Hess's law to this reaction. You're given a set of entropy values. Now, when we looked at enthalpy values, the heat content values, when we look at formation values, they start as one thing and end as another. Those formation values of elements are 0. But when we talk about absolute entropy, there is no absolute entropy. There's always, or there's no 0 absolute entropy. There will be some motion and disorder and chaos that exists in all matter. So there is entropy in all matter. There's an absolute entropy value for anything. When we look at these, notice that you have your ammonia, NH3 gas, is 193 joules per mole Kelvin. That's the unit that we're using, joules per mole Kelvin. The hydrogen content is 131 joules per mole Kelvin. And then we have the nitrogen content, which was 192 joules per mole Kelvin. If I'm trying to apply Hess's law, what I'm going to do is I will double my product, so 2 times 193. I'm going to leave the units off for now because they're unchanging. I would then subtract away first the nitrogen content, which was 192. It's just times 1 this time. And I also want to consider my 3 hydrogens. So that's 3 times 131. Make sure that you do that as a combined task. You've got to get that 192 and 3 times 131 as a combined number. Take your 2 times 193, subtract away the reactant side, and when you do the math, what we should get is negative 199 joules per mole Kelvin. Now, we want to see if this makes sense rationally, because we know that if I have more moles, I have more entropy. So if I look on the left-hand side, notice that we have 1 mole of nitrogen gas and we have 3 moles of hydrogen gas, which means I have 4 reactant moles of gas. On the product side, I have 2 product moles of gas. So I'm going from 4 moles to 2 moles. Makes sense that 4 moles has a higher entropy than 2 moles, so this must be a decrease in entropy, which makes sense that it's a negative on my numeric value here. Negative 199 joules makes sense if there's a decrease in entropy. Now, I'm going to ask you to go ahead and work out this problem based upon the entropies that are given, and then you can check your work in your own mind.